2.0.0 Grounding and Bonding. Identify grounding requirements for a residential electrical system. Explain how to size the grounding electrodes. Explain how to size the main bonding jumper. Describe how to install the equipment grounding system. Grounding provides a ground fault path throughout the system so that overcurrent devices open before anyone can be hurt or equipment is damaged. In this section, you'll learn about proper grounding in a residential system. 2.1.0 Grounding and Bonding. Grounding is a major part of an electrical system. It protects people and equipment from higher than normal voltages by connecting an electrical system to the earth. Bonding is when the non-current carrying conductive parts of a system are connected together to create a conductive path. If there's a ground fault, the current can flow through the path. When the bonded elements are properly connected as shown in figure 30, the ground fault current will go back to the source. So you want all of your fault currents to run on this equipment grounding conductor, back to the grounding bus bar, through the main bonding jumper, back to the ground rod, the grounding electrode. There are two general classifications of protective grounding: system grounding and equipment grounding. Grounding and bonding requirements are covered in NEC Article 250. NEC Section 250.4 provides the general requirements for grounding and bonding of grounded electrical systems, as listed in Table 6. So electrical systems grounding is NEC Section 250.4A1. System and circuit conductors must be grounded to limit the voltages due to lightning, line surges, or unintentional contact with a higher voltage, and to stabilize the voltage to ground during normal operation. Grounding of electrical equipment, 250.4A2. Non-current carrying conductive materials enclosing electrical conductors or equipment, or forming part of the equipment, must be connected to earth to limit the voltage to ground on these materials. Bonding of electrical equipment, 250.4A3. Non-current carrying conductive materials enclosing electrical conductors or equipment or forming part of the equipment must be connected together and to the electrical supply source so that an effective ground fault path is established. Bonding of electrically conductive materials and other equipment, NEC 250.4A4. Non-current carrying electrically conductive materials likely to become energized must be connected together and to the electrical supply source in a way that creates an effective ground fault current path. Effective ground fault current path is described in 250.4A5. Electrical equipment and wiring and other electrically conductive materials likely to become energized must be installed in a way that creates a permanent low impedance circuit facilitating the operation of the overcurrent protective device. It must be capable of safely carrying the maximum ground fault current likely to be imposed on it from any point on the wiring system where a ground fault may occur to the electrical supply source. The earth must not be used as a sole equipment grounding conductor or effective ground fault current path. 2.1.1 Examining a residential grounding system. Just to better understand a complete grounding system, examine a conventional residential system such as the one used as your sample dwelling in section 1.0.0. Figure 31 shows the power company's high voltage lines and transformer. So here's the 7200 on the line side of the transformer out on the pole, and then the load side is 240 volt between A and B phase, but they have a center tapped neutral, which is grounded. It's taken to earth, and that provides a 120 volt feed from A phase to ground or B phase to ground. So one, a 2-wire single-phase 7200 system feeds the pole-mounted transformer. 2, transformer steps the system down to a 3-wire 120 240 volt single-phase electric service suitable for residential use. 3, lines A and B are ungrounded conductors, which means they're hot. 4, a third grounded conductor neutral wire on the secondary winding of the transformer connects between lines A and B. 5, the neutral wire splits the 240 in half, providing 120 volt between line A or line B and the neutral conductor. 6, 120 volt is available for lights and small appliances. 240 volts is available for household appliances such as ranges, hot water heaters, and clothes dryers. Figure 31, there's a 240 and 120 volt loads. If only 240 volt loads are connected to the transformer, the neutral carries no current. It's a balanced system. The neutral carries any ground fault currents from the load side of the service back to the utility instead of depending on the earth as the path back to the source. If there are also 120 volt loads, the neutral carries the unbalanced load and becomes a current carrying conductor. For this reason, the NEC allows the grounded conductor in an electric service to be smaller than the ungrounded conductors. However, it must be sufficient to carry fault current back to the source. This is why NEC section 250.24D1 requires that the grounded conductor, the neutral, must not be less than that required conductor size using table 250.102C1 for service conductors up to 1100 kc mil and not less than 12.5% of the area of the service entrance conductors larger than 1100 kc mil. Grounding is the systematic grounding wasn't required by the NEC until the mid-50s. Even then, electricians commonly grounded an outlet by wrapping an uninsulated wire around a cold water pipe and taping, excuse me. 3-hole receptacles with grounding terminals became common in the 1960s, but in many older houses, you cannot assume that receptacles are grounded. Even when you see a 3-hole receptacle, sometimes new receptacles have simply been screwed into the box where there's no equipment grounding conductor. Figure 32 shows the grounding connections of the panel board in the sample dwelling. NEC section 250.24A1 requires that the grounding electrode for the structure connection to the neutral, the grounded conductor, be at any accessible point from the load end of the service drop or service lateral up to and including the terminal or bus to which the neutral, the grounded service conductor, is connected to the service disconnecting means. So the grounding electrode is a big nail that we pound into the ground, a conducting object through which there is a direct connection to earth. It can be a rod, a pipe, a plate, a ring, anything in contact with the earth that will serve as the grounding electrode. Interior view of panel board showing connections. So here's the incoming pipe, the riser that has the incoming feed, A phase and B phase, and then the neutral comes over to the neutral bar. So here's A and B on the main breaker, and they come and they feed line 1, A, B, A, B, A, B, A, B. They alternate. A phase serves 1 and 2, B phase serves 3 and 4, A phase serves 5 and 6, B phase serves 7 and 8, and it just alternates like that. A, B, A, B, A, B, A, B, all the way down. The neutrals are hooked up on the neutral bars on either side of the panel. They're actually tied in common with the grounding bar because this green screw is the main bonding jumper. That's where we connect the neutral and the grounding, the equipment ground, and the grounding electrode conductor. All of them are bonded together at the main bonding jumper. So service entrance cables, underground, ungrounded conductors, service 12240 hot wires. That's these two. 3 is the main disconnect switch. That's there. 4 is the 120 volt loads. 5 is 240 volt loads. So here's a 120 volt load. Here's a 240 volt load on a 2-pole breaker, A and B phase. 6 is the grounded conductor, the neutral. Here's 6. 7 is the panel board itself. That's this whole thing. 8 is the neutral or ground bar. That's this one and this one. 9 is the grounding electrode conductor. So here's 9, it's going out to the ground rod, and 10 is the main bonding jumper. Here's the main bonding jumper. The term effectively grounded means equipment is intentionally connected to earth through one or more ground connections. Connections must be of sufficiently low impedance and have sufficient current carrying capacity to prevent the buildup of voltages that may result in a hazard to people or connected equipment. 2.1.2 Using grounding electrodes. You can find the requirements for connecting an electric service to the grounding electrode system or of a building or structure in NEC Article 250 Part 3. In general, NEC Section 250.50 requires that you bond together any of the grounding electrodes described in NEC Section 250.52a to form the grounding electrode system. The electrodes listed in NEC Section 250.52a are as follows. Metal underground water pipe in direct contact with the earth for at least 10 feet and electrically continuous, or made electrically continuous by bonding around insulating joints or insulating pipe. Metal in-ground support structure that complies with NEC Section 250.52a2. So that's any kind of rod iron, or spikes that are in the ground. An electrode encased by at least 2 inches of concrete may be used if located within and near the bottom of the concrete foundation or footing in direct contact with the earth. And the electrode must be at least 20 feet long and made of electrically conductive coated steel, reinforced bars or rods not less than 1/2 inch in diameter. A grounding ring that encircles the building or structure. The ring must be in direct contact with the earth, consisting of at least 20 feet of bare copper conductor not smaller than number 2 gauge, see NEC Section 250.52a4. Per NEC Section 250.52a5, rod and pipe electrodes must not be less than 8 feet in length and consist of either pipe or conduit not smaller than tray size 3/4 inch or metric designator 21, and whereof iron or steel shall have an outer surface galvanized or otherwise metal coated for corrosion protection. Rods of stainless steel and copper zinc coated steel shall be at least 5/8 inches in diameter unless listed. Plate electrodes with their surface exposed not less than 2 square feet to exterior soil. Plates made of iron or steel shall be at least 1/4 inch thick. Non-ferrous metal plates shall be at least 0.006 inches thick. See Section 250.52a7. Per NEC Section 250.52a8, other local metal underground systems or structures such as piping systems and underground tanks that are not bonded to a metal water pipe. Now, water pipes have to be part of the grounding system, but they cannot be the sole grounding electrode. Water pipes have to be supplemented by at least one other electrode. You cannot use the water, cold water, as the only grounding electrode. Gas lines that are metal pipe underground cannot be used as a grounding electrode, but they must be bonded with at least a number 6 gauge wire attached to the gas pipe. So here they're showing 6 is a grounding rod, 5 is a metal cold water pipe, 4 is the grounding clamp, 3 is the grounding electrode conductor, 7 is the concrete encased electrode, that's an OOFR ground, and then here's 8. This is metal underground gas piping system. Look what they have here, the red slash through the circle. Some areas require 2 grounding electrodes spaced more than 6 feet apart. And this gas pipe cannot be used. It says this house has a metal underground gas piping system, but this may not be used as an electrode. But it does have to be bonded. Often the residential construction, the only grounding electrode available is the metal underground water piping system. NEC section 250.53D2 requires that whenever water piping is used as an electrode, you must supplement it with another electrode. You can use any of the electrodes listed above. Rod, pipe, plate. There's a note, some authorities having jurisdiction do not recognize water piping as an electrode. This is because non-metallic piping is used more now for both new and replacement water systems. Instead, they require the use of other electrodes, such as a concrete encased or rod electrode. To make sure concrete encased electrodes are available, electricians must be involved with the construction prior to the foundation being poured. What do you do if water pipe, building steel, and concrete encased electrodes are not available? Well, you're going to have to get to the building steel somehow. All right. Warning: metal underground gas piping system must never be used as a grounding electrode. It would pose a significant risk of explosion. 2.1.3 Grounding electrode installations. NEC 250.53A1 requires rod, pipe, and plate electrodes, where practical, to be buried below the permanent moisture level and free from any non-conductive coatings such as paint or enamel. NEC section 250.53A4 permits a rod or pipe electrode to be driven at a 45-degree angle if rock bottom is encountered and prevents the rod or pipe from being driven vertically from at least 8 feet. Where driving a rod or pipe electrode at a 45-degree angle will not work, it is permitted to lay a rod or pipe horizontally in a trench that is at least 30 inches deep. For rod or pipe electrodes longer than 8 feet, it is permitted to have the upper end of the ground rod level with a suitable means of protection is provided for the grounding electrode conductor attachment. Otherwise, the upper end must be flush with or below the Earth's surface. Okay. Oh, let's see here. It says NEC section 250.53A2 requires a supplemental electrode when a single rod, pipe, or plate electrode of a type specified in NEC section 250.52A2 through A8 is used. If a single rod or pipe grounding electrode has a resistance of 25 ohms or less is used, the supplemental electrode shall not be required. But if it has a resistance of higher than 25 ohms to ground, you have to have a supplemental ground rod. Always check with the local inspection authority, including the local utility, for rules that surpass the requirements of the NEC. Some general rules are as follows. Where multiple rod, pipe, or plate electrodes are installed to meet the requirements of this section, they shall not be less than 6 feet apart. Plate electrodes must be buried at least 30 inches below the surface of the Earth. And where 2 or more electrodes are effectively bonded together, they are treated as a single electrode system. Grounding electrode conductor. This is the conductor that goes from the grounding electrode to the panel. A grounding electrode conductor connects the grounding electrode to the system grounding conductor or equipment. Grounded, excuse me. NEC section 250.62 covers the requirements for grounding electrode conductors that connect to neutral grounded conductor. At the panel board, neutral bus to the grounding electrodes. The following summarizes those NEC rules. The grounding electrode conductor must be made of copper, aluminum, or copper-clad aluminum. The grounding electrode conductor must be protected against corrosion. Grounding electrode conductor may be either solid or stranded and insulated, covered, or bare. And because the grounding electrode conductor is not an equipment grounding conductor, it does not have to be identified using the color green or green with yellow stripes if insulated. All right. 2.1.5 Installing grounding electrode conductors. You'll find that the installation requirements for grounding electrode conductors in section 250.64. The do's and don'ts of grounding electrode conductor installation are as shown in figure 35. Residential wiring do's and don'ts. Securely fasten the grounding electrode conductor or its enclosure to the surface on which it is carried. Protect a number 6 gauge or large copper or aluminum grounding electrode conductor if it will be exposed to severe physical damage. Make sure metal raceways for the grounding electrode conductor are electrically continuous by bonding each end of the raceway to the grounding electrode conductor. A number 6 gauge or larger grounding electrode conductor that is subject to physical damage, or a grounding electrode conductor smaller than number 6 gauge, should be installed in rigid metal conduit, intermediate metal conduit, Schedule 80 PVC, EMT, RTRC, or cable armor. Only run a number 6 gauge or larger grounding electrode conductor that is free from exposure to physical damage along the surface of the building without metal covering or protection if it is securely fastened to the building. Do not use bare aluminum or copper-clad aluminum grounding conductors if they will be outside within 18 inches of the earth at the termination point. Do not use bare aluminum or copper-clad aluminum grounding conductors if they will be in direct contact with concrete. Do not use bare aluminum or copper-clad aluminum grounding conductors if they will be subject to corrosive conditions. Ferrous metal enclosures for the grounding electrode conductor that are not physically continuous from a metal cabinet or a metallic equipment enclosure to the grounding electrode must be made electrically continuous by bonding each to the enclosed grounding electrode conductor. Service bonding methods must comply with NEC Section 250.92A for installation at service equipment locations and with the methods used in NEC Section 250.92 B2 through B4. Here are some best practices for installation. Run grounding electrode conductors to any convenient grounding electrode available in the grounding electrode system or to one or more grounding electrodes individually. Size the grounding electrode conductor for a largest grounding electrode conductor required. If the interconnected, make sure each type of electrode has its maximum size grounding electrode conductor. The largest size grounding electrode conductor can be run to all electrodes. Install the grounding electrode conductor in one continuous length without a splice or joint unless it meets the requirements of NEC Section 250.64 C1 through C4. Connecting grounding electrode conductors, NEC Section 250.70 requires that the grounding electrode conductor must be connected to electrodes using exothermic welding, listed pressure connectors, listed clamps, listed lugs, or other listed means. You must never use connections that depend on solder. To prevent corrosion, make sure the ground clamp is listed for the material of the grounding electrode and the grounding electrode conductor. If you use a fitting on pipe, ground rod, or other buried electrode, it must be listed for direct soil burial or concrete encasement. Figure 36 shows 4 of the approved methods for connecting the grounding electrode conductor to the grounding electrode. In general, never use a single clamp or fitting to connect more than one conductor to the grounding electrode, except when the clamp or fitting is specifically listed for this use. So here's one type of grounding electrode clamp. Here's exothermic welding. And here's an acorn clamp. Here's a city ground. So one is for indoor communication purposes only, a listed sheet metal strap type ground clamp with a rigid metal base that sits on the electrode with this strap that will not stretch during or after installation. Number 2, a listed bolted clamp of cast iron or brass or plain or malleable iron. We call that an acorn clamp because it looks sort of like an acorn. 3 is a pipe fitting, pipe lug, or other approved device that is screwed onto the end of a rigid pipe, otherwise known as a city ground. And 4 example of an exothermic weld to a grounding rod. Figure 37 shows that you must make sure the connection of a grounding electrode conductor or a bonding jumper to a grounding electrode is accessible unless the connection is to the concrete encased or buried grounding electrode permitted in Section 250.68. Where it's necessary to ensure the grounding path for metal piping used as a grounding electrode, effective bonding shall be provided around insulated joints and any equipment likely to be disconnected for repair or replacement. Bonding conductors shall be of sufficient length to permit removal of such equipment while retaining the integrity of the bond. 2.1.7, sizing the grounding electrode conductor. That's 250.66. There are strict rules for sizing grounding electrode conductors. NEC section 250.66 requires you to use the area of the largest service entrance conductor or the equivalent area for parallel conductors. Use NEC table 250.66 to find the minimum size grounding electrode conductor at any bonding jumpers you need to interconnect grounding electrodes. There are some exceptions to which are listed as follows. Okay. Where connected to rod, pipe, or plate electrodes, the portion of the grounding electrode conductor that is the sole connection to the grounding electrode shall not be required to be larger than number 6 gauge copper or number 4 aluminum. We were saying before that an underground gas pipe cannot be used as a grounding electrode, but you have to take a minimum of a number 6 bond to that metal gas pipe. It has to be bonded. Where connected to a concrete encased electrode, that portion of the grounding electrode conductor that is the sole connection to the grounding electrode shall not be required to be larger than number 4 gauge copper. Where the grounding electrode conductor connected to a ground ring, the portion of the conductor that is the sole connection to the grounding electrode shall not be required to be larger than the conductor used for the grounding ring. Where multiple sets of service entrance conductors are used as permitted in exception number 2 in NEC section 230.40, the equivalent size of the largest service entrance conductor must be determined by the largest sum of the areas of the corresponding conductors of each set. Where there are no service entrance conductors, the grounding electrode conductor size is required to be determined by the equivalent size of the largest service entrance conductor required for the load to be served. Okay. 2.1.8, air terminals. These are lightning rods. They're about 3 feet long. They're little ones. In some situations, according to NEC section 250.60, you might use air terminal conductors and driven pipes, rods, or plate electrodes for grounding air terminals. You cannot use them in place of the grounding electrodes covered in NEC section 250.50 for grounding wiring systems and equipment. However, NEC section 250.106 requires that you bond them to the structure's wiring and equipment grounding electrode system. Okay. Main bonding jumper. Yeah, I almost think we should read the definition of the main bonding jumper in the code book. Let's see if this tells us. Recall that bonding means connecting non-current carrying elements together to create electrical continuity and conductivity. The main bonding jumper is the conductor that connects the grounded circuit conductor, that's the neutral, and the equipment grounding conductor, that's the equipment ground. NEC section 250.24c requires that you use an unspliced main bonding jumper to connect the equipment grounding conductors and the service disconnect enclosure to the grounded conductor of the system within the enclosure of each service disconnect. Additional requirements for a main bonding jumper are as follows. The main bonding jumper must be made of copper, aluminum, copper-clad aluminum, or other corrosion-resistant material per NEC section 250.28a. A main bonding jumper may be in the form of a wire, a bus, a screw, or similar suitable conductor. If the main bonding jumper is a screw, it must have a green finish so that the head of the screw is visible for inspection. You must attach a main bonding jumper using exothermic welding, a listed pressure connector, listed clamps, or other listed means. The main bonding jumper cannot be smaller than the size given in table 250.102C1. See notes 1 and 2 from table 250.102C1 for service conductors that exceed 1100 kcmil. It's 12.5%. Size for supply conductors in a single raceway or cable, 250.102C1. Rounded conductor main bonding jumper, system bonding jumper, and supply side bonding jumper for alternating current systems, 250.102C1. Did you know lightning rods? An interesting fact about grounding is that a lightning rod isn't meant to bring a bolt of lightning to ground. To do this, its conductors would have to be several feet, 1 meter or more, in diameter. The purpose of the rod is to dissipate the negative static charge that would cause the positive lightning charge to strike the house. The main bonding jumper allows any ground fault in branch circuit and feeder of the electrical system to travel back to the source of supply at the utility. A ground fault will travel along the equipment ground conductors of the circuit back to the service disconnecting means. Where metallic raceways are used as equipment grounding conductors, there will be no connection to the grounded conductor at the service. Without the main bonding jumper, the path back to the source would be through the grounding electrode system and the earth. This does not provide a low impedance path and thus will not allow enough current to flow in the circuit to let the overcurrent devices open. The main bonding jumper provides the path back to the source for faults that occur within the service disconnecting means. So, for example, suppose that a phase conductor makes contact with the metallic housing of a 120 volt 15 amp appliance that was wired using EMT. When you total the combined resistance of the EMT with the resistance of the metal water piping and the ground rod in the sample house, you get 20 ohms. This is less than the 25 ohms permitted in exception from NEC section 250-53A2. The amount of current that could flow back to the utility source would be calculated using Ohm's law. So E divided by R equals I. So 120 divided by 20 ohms is 6 amps. The smallest overcurrent device in the sample dwelling's electrical system is 15 amps and would not trip. With the main bonding jumper installed, the path back to the utility source is through the main bonding jumper to the grounded conductor of the service. This resistance will be much less than 1 ohm, and thus would allow enough current to flow to open the overcurrent device within the system. Bonding at the service. Electrical continuity is necessary to make sure the system is safely grounded. NEC section 250.92a requires electrical continuity at the service. It states that the following must be bonded: the service raceways, the auxiliary gutters, or service cable armor or sheath, except for underground metallic sheaths of continuously underground cable, as noted in section 250.1.84. All service enclosures containing service entrance conductors, including metal meter fittings, boxes, or the like, interposed in the service raceway or armor. Any metallic raceway or armor enclosing a grounding electrode conductor according to NEC section 250.64e. The NEC states that you must apply bonding to all intervening raceways, boxes, and enclosures between the service equipment and the grounding electrode. The items that typically require bonding include the mast and weatherhead, the meter enclosure, the armor of the service entrance cable, if it has armor, and the service disconnect. Methods of bonding at the service. NEC section 250.92b includes the following methods that should be used to ensure the electrical continuity of the service equipment, raceway, and enclosures. Bonding equipment to the grounded service conductor in agreement with section 250.8a. Connections using threaded couplings or threaded bosses on enclosures when made wrench tight. Threadless couplings and connectors when made tight for metal raceways and metal clad cables. And other approved devices such as bonding type lock nuts or bonding bushings. 2.2.3 Bonding and grounding requirements for other systems. NEC section 250.94a sets the rules for inter-system bonding terminations. It states that you must have an inter-system bonding termination for connecting inter-system bonding conductors. It must be external to the service equipment enclosure or metering equipment enclosure, and if there are other buildings or structures, it must be at the disconnecting means. Inter-system means that the electrical system and other systems such as communications, radio, and television, community antenna television, and network-powered broadband communication systems are bonded together. The intersystem bonding termination must meet the requirements listed in NEC section 250.94a. 2.2.4 Bonding of water piping systems. NEC section 250.104a sets the rules for how to bond a metallic water piping system. You must bond the metallic water piping system using the bonding jumper. Refer to NEC table 250.102c 1 for bonding jumper sizing. The points of attachment of the bonding jumpers must be accessible. You can connect the jumper using the following: the service entrance enclosure, the grounded neutral conductor at the service, the grounding electrode conductor if large enough, the grounding electrodes in use. You must install the bonding jumpers in accordance with NEC section 250.64a, b, and e. Note that while the bonding jumper is sized in the same manner as if the water piping system is in a grounding electrode, NEC permits the point of attachment to the water piping to be at any convenient point on the water piping system and not just within the first 5 feet of where the water enters the building. Two point 2.5 Bonding of other piping systems. For how to bond other types of piping systems, including gas piping, refer to NEC section 250.104b. Any metal piping system installed in or attached to a building likely to become energized must be bonded to any of the following: the equipment grounding conductor of the circuit that is likely to energize the piping system, the service equipment enclosure, the grounded conductor at the service, the grounding electrode conductor of sufficient size, and one or more grounding electrodes used. The size of the bonding jumper is in accordance with NEC table 250.122, using the rating of the circuit that may energize the piping system. The equipment grounding conductor of the circuit that may energize the piping serves as the bonding means. The points of attachment of the bonding jumpers are accessible. 2.3.0 Installing equipment grounding system. So when we look at the code book, we're going to call this line side grounding and load side grounding. The main bonding jumper and the grounding electrode conductor are the line side grounding. The equipment grounding conductor is the load side grounding. It's the difference between table 250.66 and table 250.122. NEC Article 250 Part 4 generally requires that all metallic enclosures, raceways, and cable armors be grounded. The exceptions in NEC Section 250.80 and 86 allow metal enclosures or short sections of raceways to provide support or physical protection to be ungrounded under very specific conditions. NEC Section 250.96a requires that you remove the coating on metal piping systems to ensure that there's a permanent and effective grounding path. It also permits you to connect grounding electrode conductors and bonding jumpers at the following locations: interior metal piping located not more than 5 feet from the point of entrance of the building, as described in NEC Section 250.68c, and structural frame of the building directly connected to the ground electrode conductor. Here's a highlight. It says NEC Article 250 Part 6 covers equipment grounding and equipment grounding conductors. Here's the highlight. NEC Section 250.110 generally requires the exposed non-current carrying metal parts of fixed equipment likely to become energized to be grounded under the following conditions: where within 8 feet vertically or 5 feet horizontally of ground or grounded metal objects, where located in wet or damp locations, where in electrical contact with metal, where in hazardous locations as covered by NEC Articles 500 through 517, where supplied by a metal-clad or metal sheath raceway, or other wiring methods that provide an equipment ground. Here's the highlight. It says, where equipment operates with any terminal at over 150 volts to ground. Specific equipment required to be grounded regardless of the voltage is listed in NEC section 250.112 and includes equipment such as motors, motor controllers, and lighting fixtures. Types of cord and plug connected equipment and dwelling units required to be grounded are found in NEC section 250.114 and include equipment such as refrigerators, freezers, and air conditioners, information technology equipment, clothes washers, clothes dryers, and dishwashing machines. Refer to section 250.118 for rules on the type of equipment grounding conductors that may be used. Note that the NEC permits both flexible metal conduit and liquid-tight flexible metal conduit in certain situations. The following lists tell you when you can use the listed flexible metal conduit and liquid-tight flexible metal conduit as an equipment grounding conductor. Flexible metal conduit can be used as an equipment grounding conductor in the following situations. The conduit is terminated in fittings listed for grounding. Circuit conductors contained in the conduit are protected by overcurrent devices rated at 20 amps or less. The size of the conduit does not exceed 1.25 inches trade size. The combined length of the flexible metal conduit, flexible metal tubing, and liquid-tight flexible metal conduit in the same effective grounding fault current path does not exceed 6 feet. If the conduit is used where flexibility is necessary, a wire-type equipment grounding conductor shall be installed. The liquid-tight flexible metal conduit can be used as an equipment grounding conductor in the following situations. The conduit is terminated in fittings listed for grounding. For trade sizes 3/8 to 1/2 inch, that's metric designator 12 to 16. The circuit conductors contained in the conduit are protected by overcurrent devices rated at 20 amps or less. For trade sizes 3/4 to 1.25 inches, that's metric designator 21 through 35, the circuit conductors contained in the conduit are protected by overcurrent devices rated at 60 amps or less, and there is no flexible metal conduit, flexible metal tubing, or liquid-tight flexible metal conduit trade sizes 3/8 to 1/2 inch. Metric designator 12 to 16 in the effective ground fault current path. The combined length of flexible metal conduit, flexible metal tubing, and liquid-tight flexible metal conduit in the same effective ground fault current path does not exceed 6 feet. If the conduit is used where flexibility is necessary, a wire-type equipment grounding conductor shall be installed. Where you use external bonding jumpers to provide the continuity of a fault current path, NEC section 250.102E2 limits the length of not more than 6 feet. The exception is in outside pole locations for the purpose of bonding or grounding the isolated sections of metal raceways or elbows installed in exposed risers at those pole locations. When you install an equipment grounding conductor in a raceway, Table 250.122 determines the size of the equipment grounding conductor. NEC permits you to install one equipment grounding conductor in a raceway that has several circuits. In that case, you must base the size of the equipment grounding conductor on the rating of the largest overcurrent device protecting the circuits contained in the raceway. NEC section 250.148 requires that where you splice circuit conductors within a box or where they terminate on equipment within a supported by a box, you must splice or join all equipment grounding conductors associated with those circuit conductors within the box or the box with device suitable for that use. Table 7 illustrates the types of fittings. Figure 39 shows different equipment grounding methods. So here's a grounding screw, here's a grounding wedge, grounding clip, a grounding U-bolt, a grounding clamp, and a bonding bushing. Equipment grounding methods, here's the grounding clamp, here's a lug, here's a ground screw, and these are all joined together. Splices, grounding screw, 2.0.0 section review. Well, when used as a grounding electrode, a ground ring must be at least how deep or how long? When a screw is used as a main bonding jumper, its finish color must be what color? And information on equipment grounding for computers is found where? Okay, so that's it for this video, and I'll meet up with you on the next video.